All right. How we doing with everything so far? Like, is there any question
There's one.
on any homework that you need to get straight?
Oh wait, I had it.
Because you don't want to get behind on any of this. Right now we're arithmetic, geometric. We're going to do, actually, in my opinion, something that's kind of easy today, although the understanding of it's going to bother some of your brains. I think that's kind of fun.
Wait, are we adding like infinite or?
Yeah, we're going to do some infinite geometrics, but the math of it's even more simple than adding finite sequences. You had a question?
I had.
Go ahead.
I had
one
number
was the
34.
answer.
Number 34.
Do you remember what it was?
I do
Like
not.
estimate that one?
Yeah.
Oh
Yeah, it was like estimate with the, it was like n is a very large number.
And it was like R to the N,
R
and then
is
it
a
was
very
like,
small number.
Okay, what page was it?
five-
No,
529. 529. No, 528.
528, number
34.
Okay, so they're heading towards what we're doing today. So they basically said, if R is a number smaller than 1 and bigger than -1. So it's a decimal whose denominator, it's a decimal in between there, or it's a fraction whose denominator is bigger than the numerator. Are you with me? Okay, so it says, what happens if n is huge? So n basically is going towards infinity. It's getting very big. What would happen to the value of this expression? This is really what we're talking about today. So if you missed that, no worries. Now, how about we just pick a number in between here? And by the way, 0 doesn't work because the whole definition of geometric sequences is that the ratio isn't 0. Because if the ratio is 0, what happens to your sequence? 0, 0, 0, right? It doesn't do much. So it's not very exponential at that point. So any number other than 0 between these two. So how about something like a half? A half is in between there, right? So what would happen to a half as I start changing the power towards something really big? So let's think about a half. We'll start with 1, all right? 0.5. What happens when I square it? 0.25. 1/4, right? What happens when I cube it? 0.125. What about to the 4th? What about to the 5th? What do you see happening to this?
You're getting smaller.
It's getting smaller, isn't it? I'm going to jump ahead a little bit to the 10th. Would be to the 100th is
A small number.
to the
Oh my.
300th. Why don't we go a little scientific notation? A TI-84, we're not going to use those. We're going to all have Inspires, unless you plan on going like the regular pre-cal, in which case it's your call. Your teachers will use 84s, but Inspire is still a better calculator. You can still drop by here and ask me questions. But to the 329th, the Inspire just quits. I'm sorry, the 84 just quits and says 0. And why? Because it only goes to 100 places. It only goes to 10 to the 100th, or 99th actually. So once it hits 10 to the 100th, it goes to the -100th, it goes so small it's negligible, smaller than an electron at that point. Oh, now is it really 0? No, you just have 100 zeros before you start hitting a non-zero number. Okay? Now the TI Inspire goes to the 999th. I'm sorry, it goes to 910 to the 999. I don't even know what that is. I haven't bothered to look on the Inspire. But the bottom line is, couldn't you assume then, logically, if the exponent approaches infinity, right? Because that's what the question was. If the exponent approaches a huge number, then what happens as that grows infinitely big? You get an infinite number of zeros. So if I keep making that bigger, I keep getting more zeros. You saw that here, right? Does that make sense? So if this grows infinitely, the zeros grow infinitely, and you never get to the numbers because there's just more zeros, right? And you can't say, well, I'll eventually hit a number. Well, wait a minute, I'm making that bigger. So are you following the logic? Now tell me, what does that do to our formula from yesterday? Our formula for finding a finite number of terms in a geometric sequence was this, wasn't it? Or it was one of them, right? What happens if your ratio, if your n goes to infinity? I literally, infinity is not a number. It's not like there's some super secret infinity number. It's more of an idea, right? That it's exploding in size. It is unbounded. So if that goes to infinity, which means you have an infinite number of zeros, as long as the r value is between -1 and 1, what happens to that number right there? What does this value become?
0.
0. And if that value becomes 0, then now I have t1 times 1 minus 0 over 1 minus r, which is just what? t1 over 1 minus r. So if your ratio is between -1 and 1, and you have an infinite number of terms, you can actually find the sum without even adding an infinite number of them, because you can't really do that, right? Now there's a better proof than this. This is just more logical thinking. The proof for this is really exactly what we did yesterday. Remember yesterday's proof? I said the sum, not the formula, but do you remember when I wrote this out?
Yeah.
And I said the sum of a sequence is the first term plus the second term plus the third term plus the fourth term. But if it's infinite, then it goes forever and there is no last term, is there? Right? Well, what happens if I multiply by a negative r? Negative s infinity r, negative t1r, remember I slid it over, negative t1r squared, because I multiplied that by r, negative t1r cubed. So what happens here if they're both going forever when you add them together?
Everything cancels out except the first.
You still get that, but everything cancels now. Because they both go forever. I don't know if you've ever done this, and if I've told this story, stop me. But I remember being a kid and sitting up in a tree. We used to climb trees. We used to go try to catch those little cicadas, you know those giant flies?
Oh, yeah.
Oh.
We would always try to catch those things. They're pretty stupid. They'll like run on the other side of the branch, and then you can just walk over there and go, and we catch them. I don't know why we like those things, but they were pretty creepy. But anyway, I remember being up in a tree with my friend, and this conversation erupted. And I'm going to say this, and you're going to go, oh my gosh, I totally had that conversation. At least some of you.
So you're in a tree, you were just chilling?
Maybe you weren't in a tree. Maybe you're like in a bedroom or something. Yeah, I was literally up in a tree. And I was like, hey man, how's your dad? How old is your dad? I was like, my dad's like 47. And I was like, my dad's 55. I had no idea how old my dad was. I was like 7 or 8 or whatever. And the guy was like, oh, actually my dad's a little older than that. He's like 66. And I was like, well, I was just kidding too. My dad's 80. And you'd go back and forth, and at some point some guy would go, well, my dad's infinity. And then you'd get the inevitable, my dad's infinity plus 1. Anyway, there is no infinity plus 1. Have y'all, anybody has that? I know, it's like it's built into your DNA. I don't know why. My kids did it. I would hear them in the back room. I was like, oh my gosh. And then I started asking you guys, and you're like, oh yeah. I don't know why that's great to make your dad the old dude, but anyway, the point is, if there's an infinite number of terms here, and you're like, well, you slid these over, so there's an extra 1. No, they're going forever. Infinity is forever. Infinity plus 1 is still infinity. Infinity times infinity isn't still infinity. Are y'all with me? So these all cancel. And all I have left is S infinity minus S infinity R. And like before, I could factor out that S infinity, right? Like I did yesterday, and divide it. And there's my sum formula again.
Whoa.
Are you seeing that? So it's the same formula we had before, but like that problem y'all just asked me about, the idea is if the ratio is between -1 and 1, R to a really high power just gets smaller and smaller and smaller. Now, it wouldn't be true if I said 2. 2 to the first is 2, 2 to the second is 4, 2 to the third is 8. Those are getting bigger. Those aren't approaching 0. So it can't be a number that's bigger than 1 or smaller than -1. That doesn't work. It has to be a fraction or a number, decimal, in between -1 and 1 so that the higher powers make it decrease in size. And if that happens, this evolves into that. So you have two formulas for the sums of geometric sequences when they're finite, or when there's a certain number of terms, and then there's one if it's infinite. But if the ratio is not between -1 and 1, you can't find the sum of an infinite geometric series. Like, so if I said find the sum here, 3 plus 6 plus 12 plus 24, ... forever and ever, you can't do it. Why? Because the sum keeps getting what? Bigger and bigger and bigger. Now you may go, well, a sum of another one might be getting bigger and bigger and bigger too, but here's the difference. Here's one, because this ratio is 2, so there is no sum. I know the temptation is to say that the sum would be infinity, but again, a sum has to be an actual number, right? Infinity is not an actual number, it's more of an idea, right? That something is getting bigger and bigger, right? So you just can't do it by rule. You would just say there is no sum here. But if I gave you this, what's happening here? But I'm still adding stuff, right? But what's my ratio? So my ratio is between -1 and 1. And because it is, even though I'm adding stuff, the stuff I'm adding is smaller and smaller and smaller and smaller and smaller. And that means I'm adding a more negligible amount. Okay? So what happens here is this sum is what we call a diverging sum. Because it's divergent, it's as opposed to a converging sum. This is converging on a value. I'll illustrate it like this. What if what if I told you to start over here and walk half the length of the room and stop, and then walk, or half the distance from here to the wall and stop. And then I say, okay, now walk another half and then stop. And then walk another half. So the first thing I do is I walk over here and I walk half the length of the room and I stop. All right, then I'm going to add to that, here, I'll write it over here. So that's the first 1/2, okay? Right here. And then I'm going to go half of the remaining half, which would be how much? 1/4. So I walk to right there. And so I've now I've walked half the length of the room and 1/4 the length of the room, right? Now I'm going to walk half of the remaining 1/4, which is what? An 8. So I walk to there, and that's adding an 1/8, right? And then once I'm here, I walk half of the remaining 1/8, which is a 16th, and then a 1/32, and then a 1/64, and then a 1/128, and 1/252, and I keep going half, 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 half. Will I ever hit the door?
No.
Yes. And that's what bothers everybody. But here's why. It would take me forever. I would have to go forever to hit the door. And that is beyond the scope of our brains. We don't do anything in forever. Now, I know what you're saying. What you're thinking right now is, no, you don't. Because at any point, if I get my ruler out and stop and measure, there's still a little bit of half left over. Right? That's what you're thinking. What did I have to do to measure?
Put a ruler
The
there.
ruler put it there.
What did I have to do? Stop. And if I stop to measure, I am only calculating a finite number of moves. Are you with me? Are you seeing that? So if I stop, you're right. Like if I go 99 of these halves, like if I just keep going, right? And I keep going for a bunch, but I stop at the 99th term. I mean, that's gonna be a really small number, right? And I stop and measure. No, this is not equal to the whole length of the room. There's a little bit left. But if I go forever, I'll get there. Now, what should I end up with then if I get there?
0.
One length of the room, right? Well, let's see how my formula works.
That's what I guess.
First term over 1 minus the ratio. Huh. So it works.
But what about that graph? You know, the one that goes like that, and it like never hits the axis that you're talking about.
And you're right, each individual term right here is only approaching 0. You're talking about an individual, so at any particular point, like on a 1 over x graph, is maybe what you're thinking, that does that, you know, the broken fan director or whatever, is that what you're talking about?
Yeah.
So at an asymptote, you are getting closer and closer and closer, that individual asymptote. But that's a term. That's like these terms. I'm getting closer and closer to 0, right? On these. But the sum, and it's approaching 0 when I go to infinity. I can use that logic. So I could also use that logic and say I'm approaching it as I get there. But the sum of them is what we're talking about. And the sum of these, it will work. Mainly because I proved it. Now the 99th term, if I just go to the 99th, I gotta tweak my formula, right? First term, 1 minus r to the 99th power over 1 minus a half. And if I do that, I think my Inspire can do that. So if I go to the 99th, I get fraction button 1 half parentheses 1 minus parentheses 1 half 2d. I hope it doesn't bail on me. It shouldn't. Sometimes it goes, oh man, 0 or whatever. Okay, so it gives me, it spit out 1.
Wait, but
It
isn't
spit
that-
out 1, but it's not. It's just my calculator.
Wait, what do you?
Rounds to 5 decimals, and the thing is so small, so it's rounding for me, and I can't seem to get that exact value. I could probably go and graph something, and if I graphed this and went out to a value of 99, I could probably get somewhat of a scientific notation, but the bottom line is it's really close to 1. But in this case, if I only went out to the 99th place, I would use that different formula. This one spits out 1 because it rounds, but it wouldn't be. It would really be 0.9999999999999 way out, and then the numbers would start changing at the end. But if I go forever, the sum of these, I can get to the door. I just have to go forever. And our brain doesn't think that way. Because name one thing in your life that's actually infinite. And don't throw stuff like my love for my parents, or you know, the grains of sand on the seashore. I mean, those kinds of things, even the grains of sand. Give me enough time, right? And I can do it, right? And stars in the sky. I mean, there's countable stars for me. You know, there's nothing, I mean, you could keep going in theory, right? I mean, we assume that there's more out there, and we've sent Hubble telescopes, you know, and they're still getting information from, you know, information that star sent out hundreds and hundreds of years ago, and the light is just making it back to us. I mean, weird stuff like that, but the bottom line is our lives are very finite, so it's hard to wrap around the, wait a minute, I'm not gonna get there. There's always gonna be a little bit left. Well, you stopped to measure. And if you stop, it's finite. And this is not 1, it's just really, really close. But if you go forever, you can, and you proved it, right? Did we talk about the 1/3 plus the 2/3? Have I mentioned that?
Oh yeah, I love that.
Have I shown you all that?
The
Yeah, like y is 1 equal to 0.9. Okay, and this is gonna help you maybe wrap your brain around it too, if I haven't mentioned this. like, everybody would agree that 1/3 plus 2/3 is 1. Not a lot of argument there, right? But I think everybody also would agree that 1/3 is 0.3 repeating, 2/3 is 0.6 repeating, right? So what would that give me? 0.9 repeating? So you just said that 0.9 repeating is 1. Now, guess what 0.9 repeating really is? 0.9 repeating is 0.9 plus 0.09 plus 0.009 plus 0.0009 forever and ever, right? Does that make sense? That is 9/10 plus 9/100 plus 9/1000 plus 9/10,000. What do I have here?
The rate is just 1.
The rate is 1/10. You have a geometric series whose ratio is, you multiply the top by 1 and the bottom by 10, or if you put that over that and simplify, you get 1/10. 1/10 is in between -1 and 1, right? So my sum is the first term over 1 minus the ratio, 9/10 over 9/10. I mean, this all plays out and works. It may bother you, and if it still bothers you and you're like, I don't buy it, that's okay too. But definitely buy it on my test. So if it's geometric, right, and your ratio is between -1 and 1, right, then you can add infinite series. That's the only one you know so far. You cannot add infinite arithmetics. You cannot. If you ever are asked to, if I ever say 10 plus 5 plus 0 plus -5, whatever, or 2 plus, 7 plus 12 plus, you can't add them. No sum. There's arithmetic. There's no way. Why? Because the values are diverging. They're getting bigger and bigger and bigger and bigger, as opposed to converging on a single value. Like when I was walking the room, I was converging on what? The length of the room. I was getting closer and closer and closer, right? So it's almost like there was a limit. There was an end to where I was going. Whereas if I keep adding stuff, I just getting bigger, bigger, bigger. Or if I multiply by a ratio bigger than 1, or smaller than -1, I get bigger and bigger and bigger and bigger and bigger. Can't add those. All right? And you're going to learn how to add other infinite ones before we take our test next Wednesday. Some of them I call strange sums, and they're weird little math team questions that pop up quite often, actually. And we're going to learn some other ones. But for arithmetic geometric, which is the core of what we do in Algebra 2, the other stuff's kind of math teeny. Just remember that formula. It's pretty simple. It's a lot easier than this other one, right? That's a lot easier than that. But I can do this under those conditions. Y'all seeing it? Now, let me show you a problem. It's probably so if you ever see something and you identify it as geometric, and you notice the ratio is between -1 and 1, and it's infinite, you always can find the sum. I'll give you a couple, and then I'll show you probably the most common infinite geometric question ever asked. It's maybe it's a little tricky if you're not paying attention, but anyway, let me just give you a couple. What about this? So you get that on your test. Clearly it's telling you to add. Is it arithmetic or geometric? How do you know? Because that over that's 1/5. And if you have to check, 2/5 over 2 means 2/5 times the reciprocal of 2. And that's also 1/5, right? So I know what the ratio is 1/5. And 1/5 is definitely in between -1 and 1, right? So what can I do? I can find the sum, and what is the sum of all the terms here?
1.
First term, which is 10.
1. Wait, 10.
I got it. So first term is 10,
Not 1.
1 minus the ratio on the bottom. So I get 10 divided by 1 minus 1/5 is 4/5. And how do you divide by a 4/5?
54.
You multiply by 5/4, so you get 50 over 4, which is 25 halves. Not too bad? All right, what about this one? What if I said 32 minus 8 plus 2 minus dot, dot, dot? Is this geometric?
Yeah.
How do you know?
1/4.
Because you check the ratio, right? That over that is negative 1/4. That over that is negative 1/4. So my ratio is negative 1/4. And if my ratio is negative 1/4, it's in between negative 1 and 1. I can add this, the infinite terms, right? How do I do it? 32 on the top, 1 minus a negative 1/4. And what is 1 minus a negative?
Plus.
5/4.
So 32 over 1 plus 1/4, which is 5/4. And how do you divide by a 5/4? Multiply it by a 4/5. Nothing cancels there. 1/28. Y'all seen this? Okay, how about this? World's most common word problem at a math tournament. It's geometric. What if a dude throws a ball, say Biff throws a ball upward 100 feet, and each time it hits the ground, it rebounds 3/4 of its height. How about of its fall? Does that make sense? Of the amount it fell. So what's happening here? I'm going to draw a little picture. I'm going to assume that he threw it straight up, but I'm going to draw the picture kind of going to the right so you kind of see the bounces here. So if this is the ground here, I'm throwing it up 100, but it's also doing what? Falling 100. So it's gone 200. Oh, I didn't ask a question. What is the total vertical distance traveled? So basically, what's the sum of all the ups and downs? So on the first up down, I've gone what? 200 feet. But then it's going to rebound 3/4 of what it fell. It fell 100 feet. What's 3/4 of that?
75.
Oh, sorry.
75, right? So, and you're not even going to have to know that after you do this, because you don't need to know anything but the first term if it's infinite. So it's going to come, but I'll write it anyway. It's going to go bounce back up 75, but it's also coming down 75, right? And then what's it going to do? 3/4 of that. So whatever 3/4 of 75 is, which is not 225/4, but if there's some other number, right? And it's going to keep doing that. Now, if it always rebounds 3/4 of its fall, in theory, isn't it going to keep coming back up and bouncing forever? So if it's going to keep bouncing forever, what can I use here? This to me looks a whole lot like the first term is 200. The next is, so to me this looks like a 200, 150, whatever the next one is, yada, yada, yada. Doesn't that feel very geometric to me? I mean, because what you did to get to the next term is you multiplied by 3/4. Isn't that what you did? And if I'm multiplying by 3/4 each time, this to me seems like an infinite geometric sequence. Now, if you're thinking to yourself, Mr. Hurry, so there's this ball in my backyard that I threw about a week ago. Does that mean is it still bouncing? Well, we have things called friction, right? And if you haven't taken physics yet, but if you take physics here or anywhere, you'll learn that nothing's perfectly elastic. Okay, so like, you know those little rubber bouncy balls that you could throw against the ground, they go a mile high? Okay, those are very elastic. Pool balls, when they bounce off of a pool table, very elastic move, so you can really kind of measure the angles because they're going to come off very geometrically. Okay, but most things have friction, in fact, including those two. There's friction, and that friction, there's friction in the air. If you don't believe me, drop a sheet of paper and drop this pen. What's going to hit the ground first?
The pen.
Why? Because the air is slowing down the paper, right? I mean, if I drop that's true for almost anything. If I drop a wadded up piece of paper, it's going to drop faster, but it has friction there. Air has friction. If it didn't, you wouldn't be able to curve balls when you pitch them. You wouldn't be able to hit further at Mile High Stadium or in Coors Field out in Colorado. Like, if you go out, the batting averages are always better out in Coors Field in Colorado for the Rockies. Why is that? Because the pitches don't break as much, the air's so thin, and the ball, when you hit it, goes a lot further. So pitchers, I do not want to pitch there. Like, they don't want to go play for the Rockies because their stats are going to be terrible. And hitters love to hit there, you know, just because they can hit so much better and so much further, and the pitches aren't as good. Anyway, bottom line is there's friction that changes this, but in the absence of that friction, the ball would be bouncing forever. If you're swinging on a swing, you know how you slow down over time? Right? Well, without friction, you'd slow down, but you'd swing forever. But that little joint up at the top has friction up there. You can hear it creaking sometimes. Whatever. Anyway, so we can think about this as an infinite geometric sum. So how would you do it? What's your first term?
100.
But really, you went up. Now, you could do this. You could say, well, all my ups, you could say this. I had 100, and then to get 75, I took 100 times 3/4. And then to get to that next one, I could do 100 times 3/4 twice. And I could keep doing this forever. But that's only going to calculate the ups, right? I'm also doing the downs. But if you want to do them separately, you could say first term, this would be going up. You could say first term over 1 minus the ratio, 3/4. And that's all the ups. But then you'd also have to do the same thing for the downs, wouldn't you? So if you want to do that, you could.
Just double.
I would just assume we just double it and go 2 times the 100. Treat these like individual terms. So treat it like 200, 150, whatever the heck that is. And then you can still go 1 minus the 3/4. Does that make sense? Now, this is actually not the most common question. This is what I teach before the most common question to make sure you're okay. The most common question is, Biff drops a ball from a height of 100 feet. So, I didn't throw it up. I just dropped it. So what would you do?
You do the same
Lots of
thing,
options.
but then just subtract 100.
That's what I would do. He said, do the same thing, which overcalculates, right? So like if I do 2 times 100, and I'm basically saying, oh, I'm going to forget the fact that he dropped it, I'm going to pretend he threw it. So I'm going to pretend it's still 100, 100. That's this. But since I really didn't throw it up, I just dropped it from up here, that never existed, did it? So let's take that part off. That's what I do because I think it's easier. Now some people go, nope, not a fan of that. So some people think, well, why don't I do the ups? The ups never had that first 100. So what you could do if you did the ups is just not start at 100, start at what?
75.
75, and then when you do the downs, start at 100. So you could do that in this case. Or you could just completely forget about the first 100 and say, I'm going to start with the 75s. So I'm going to go 2 times the 75 over 1 minus 3/4. And that's the first time I start going up and down. And then just do what? Add 100. So there's all kinds of options for you on how you could do it. I don't care what you do, but I cannot think of a time I have not asked this question on a test. So you can expect to see it. And you'll probably, if we had 3 or 4 math tournaments, you'd probably see that question 3 or 4 times. I mean, it's very common. It'd be a ciphering question or a written test question. And then sometimes they tweak it a little bit to mess with you. But anyway. But that's probably the most common little bouncy ball problem that you'll see. You're gonna see some tonight like swinging pendulums. You know, like a grandfather's clock that's slowly swinging, and they give you the first swing, and then it swings back 90% of its swing. So that's not like over back. It doesn't do that, right? Like if you're on a swing, you don't go 15 feet, and then decide. It's like 15, 14, 13 something.
Don't double it.
Do what? There would not be any doubling on that. Does that make sense? Because you're slowing down the whole time, so the swing is slowing on each back and forth, right? Not back, forth, then slow down. But on an up, down, it makes sense. Whatever you go up, it's going to come down, right? Does that make sense?
Oh, I know.
How did you?
I'm
That's what
ready.
he said before class, he said there's gonna be a power.
No, I said like.
I'm
Yes.
ready.
You ready, Isaac?
Nobody's so bad.
I love it. All I have to do is sniff, you know, like.
This one's 21 inches.
All right, no peeking.
7 and 65.
Don't flip it over.
So did I.
I haven't studied these in so long.
I just know about those things. I'm trying to study about
No, that's 6 is.
Don't do it.
6:25.
That's no.
5, 25, 6, 25.
5:25, 6:25.
No, 5, 25, 125.
Hey, what's the one after 13?
13, 125.
This is a big grade.
Don't flip them yet.
13, 125.
31, 31.
No, it's 3,
Yeah,
yeah.
it was 15, 65.
Yeah, 3, 1, 3, 1, 3, 1.
It's 3 to the fifth, the
15,
fourth, the
What's that, 5?
Wait, what's this?
15, 6, 25.
Yeah.
You ready, Isaac?
Oh, yeah.
No. 65, 65.
Yeah. Okay. Told you.
Oh, yeah.
It's gonna be.
Want the name.
Wait, what is it? What did you say?
Oh, I'm looking for my phone.
Okay.
Like an idiot.
15, 625.
Like, where did I put it?